Okay, so first of all, I'd like to thank the organizers for inviting me to this workshop and giving me the opportunity to present some works that I have been doing in recent years. And also, although I'm participating remotely, I have been actually enjoying the many talks given by the speakers so far. So thank you. So today I'm going to talk about some gravity. So we have seen this gravity, say, water wave from the first talk. And here I'm going to talk about the gravity in more like an astrophysical fluid context. So let me start with some picture. So this is the some image of supernova taken by NASA. And so I think of let's say this supernova as some astrophysical object which we can actually use fluid or gas dynamical equations to try to analyze some solutions and try to see the behavior, right? And so as you can see from this image, maybe the image tells us that, okay, so this is like fluid-like, gas-like, right? And also the shape is quite round. So I say this because most of the new results today I'm going to talk about will have come with spherical symmetry. So let me so then go into the question. So how do we actually study this astrophysical object in mathematical terms, right? So the mathematical star, or let's actually mathematical star is let's say is some compactly or some object, isolated object, either compactly supported or having the fast decay at infinity, where it has gravity or is self-gravitation, right? So in astrophysics context, one classical model to describe this dynamics of gaseous star with the Newtonian gravity is given by this Euler-Poisson system. Here, rho is the density, and u is the velocity, p is the pressure, and gravitational potential given by phi. So here, I'm thinking about the stars are compressible fluids, so gaseous stars. So density could change. It could contract, or it could expand, or it could oscillate, right? So this is compressible Euler-Poisson system, and first equation is continuity equation that we have seen throughout this workshop, and the second equation is momentum equation. Once again, like in the first talk, like Suji tell us that this is actually forces, right? So there is a pressure gradient, and here the self-gravitation is given by the gravitational potential will satisfy this Poisson equation. So it's B is really Newtonian gravitational potential. So there are many unknowns, and we have more unknowns than, let's say, number of equations. So in this context, we'll need the equation of state. So I'm going to focus on the very special case where P is given by a power function of the density. And here, the power gamma is usually taken between 1 and 2, and gamma 1 refer to the isothermal case, and gamma between 1 and 2, barotropic or polytropic is the word that has been used. So as we can imagine, because there are different forces in the system, we could imagine different, say, scenarios, right? Dynamical scenarios, what could happen to the solutions or to mathematical stars. So perhaps the most well-known solution to this Euler-Poisson system is the so-called Lane-Emden star, which is exactly described the hydrostatic equilibrium, where let's say its velocity is really gone, and then time-independent solutions, we are left with really pressure gradient and this gravity. So this balance is indeed studied a lot in the astrophysics literature, and Chandrasekhar, he has really the book in 1939 discussing about this Lane-Emden stars, which is essentially given by that equation that I gave you. And if we actually look at the enthalpy variable, which is given by this rho to the gamma minus 1, then that equation indeed realized as a solution to the semilinear elliptic equation, which has been also studied a lot in math literature. So this solution to this equation in this context, since we are interested in mathematical stars, it turns out that you will have a non-negative solutions in compact domain for a certain range of the gamma, exponent of gamma. And also by the Hopf lemma, of course, that behavior of this enthalpy, when this touches zero, let's say boundary of the star, then it should have some, say, the positive, say, or not negative gradient, right? Because it's coming to zero from the positive side. So this specific boundary behavior is actually, from the dynamical point of view, this is quite related to the Rayleigh-Taylor sign condition, which is actually quite important in the study of the free boundary value problem. So this understanding of this steady solution in terms of the dynamic or say evolution, right? So if I'm interested in say the existence question or Euler-Poisson's question to the Euler-Poisson system, say density or enthalpy having this specific behavior to the full Euler-Poisson system, so then I need to understand this behavior. So this actually led a very nice question about whether one can actually make sense of the solution, right? So this is now in terms of the local in time Euler-Poisson is, it's well understood, relatively well understood. So for instance, it turns out that standard, say, hyperbolic symmetrization technique will in general fail. So then turns out that the correct way of looking at the problem is indeed the moving boundary value problem. So free boundary value problem, where we actually solve the problem with this unknown, the domain. Right? So this is that particular condition is actually called now it's a physical vacuum. So now I have worked with Massimudi on the local Euler-Poissonist theory, and also there is work by Kotan and Scholar, and there's also other works by Juhi Jang and Makino and Goulet for the Euler-Poisson system. And there is also nice recent work by Ephraim Tataru, so revisiting the problem in a low regularity setting. So then once we have a local solution, of course, now one can actually ask about the dynamical stability of this Lane-Emden equation, and there is also some work. So I briefly mentioned this. So it turns out that gamma greater than 4/3, it's a linearly stable, and Gerhard Rhine, he used the variational argument to lift that linear stability to nonlinear stability by assuming the existence of solution. And gamma equal 4/3 is a critical case. So then, of course, near this ground state of the critical case, many things different scenario can happen. So Dong Liu, Yang Yao, they illustrate one way of instability. And myself also, I was looking at the other range where gamma between 4/3 and 6/5 had worked on this nonlinear instability theory. So once again, interesting numbers appears. So it turns out that one can actually do the scaling argument to realize that gamma 4/3 is indeed a mass critical case, and gamma 6/5 is an energy critical case. So then, of course, now this is all near Lane-Emden star, and one can ask whether there could be other interesting solutions, perhaps describing some physical, say, phenomena to this Euler-Poisson system. So it turns out that there's also, one can talk about some global in-time solutions, or this finite time blow solutions. So in fact, I remember 5 to 6 years ago when I was in Princeton, I was working on this paper. So we ran into a very interesting paper, very nice paper by Goldreich Weber in 1980. So they are physicists, astrophysicists, and they indeed were looking at this Euler-Poisson system with gamma 4/3 case, which is mass critical case, or in physics literature, this is also called that radiation case, has a special meaning. So then they were interested in, say, some solutions which is more or less self-similar and describing some phenomena, either collapse or expansion. So indeed, they were making this kind of ansatz, which is indeed the self-similar ansatz, rho having this form. So it's W is, I think of it as an enthalpy, once again, configuration. And this configuration is modulated by this R over lambda T. And then U takes this very special form. And this lambda T is more or less given by 1 plus T to the 2/3. So as you can see, if C is positive, then this lambda T, which I think of it as a scale of the domain, this will actually expand. So domain is expanding, and moreover, density will go to 0. So it's really the expansion or dispersion phenomena. And one can obtain these family of solutions by using this ansatz, plugging into the system, and one can obtain this as an ODE solution. So indeed, in math community, Makino in 1992 and Footlin in 1998, they indeed characterized these ODE solutions, including some other non-self-similar solutions, where this lambda T will have a different, say, behavior. The rate of expansion is different. So then when I was at Princeton 5-6 years ago, with Yahil Hazik, we were looking at some global in time stability questions of this GW or MFL, these solutions. So it turns out that this expansion has a stabilizing effect to the perturbation, nearby perturbation. So we studied this problem in the vacuum free boundary setting. And also this expansion phenomena can also be realized without gravity. So indeed, it's much more stable in the Euler case. So in fact, around the same time, Siderius, he indeed constructed very nice these affine solutions to compressible Euler equations, as well as incompressible Euler equation in the free boundary, vacuum free boundary setting. So here, we also studied the stability of this Siderius affine solution. And if we assume that small mass or small initial density, then in fact the Siderius affine solution can be perturbed under the Euler-Poisson flow. So this also has some nice global existence to this Euler-Poisson system. So then our original motivation to this global dynamics of the solution was indeed to study some collapsing, gravitational collapse, which is the blob of the gas density starting from, let's say, the smooth initial data and fluid dynamic language, and this is also called as implosion. So we were interested in this question. And mass critical case where there is a special symmetry, in fact, the solution that I briefly mentioned in the previous slide, one can actually also have the other side, and I can change the sign, and this will give us the finite time block solution. Again, the same people, Goldreich, Weber, and Markinov-Rudin, and also this has been extended by Dong, Xiang, Yang for the non-isentropic, say, Euler-Poisson case as well. And but this is again based on this similarity ansatz, and where because of the mass criticality, indeed this really becomes the ODE, one single ODE solutions. And when gamma is greater than 4/3, which is mass subcritical case, in fact, in a paper by Dong, Liu, Yang Yao in 2002, collapse by density concentration is not really possible. So it has been shown. And in a more recent work by Guichang Chen and He Wang and Yuan, they indeed prove global in time weak radial solution with finite energy when the gamma is greater than 4, and even in the supercritical regime for the small mass case. So then our motivation was, okay, in the supercritical case where this gamma is below this threshold 4/3, okay, can we actually have any example of this imploding solution or finite time gravitational collapsing solution, right? So that was the motivation. So then in 2018 with Guo and Hazik, we indeed studied this problem near the dust solution, which is a solution to the pressureless Euler-Poisson system in this regime. And more recently, between gamma, let's say gamma between 1 and 4/3, we studied the self-similar collapse, first with the gamma equal 1 case, which is known as a Larson-Penston solution. And in the full supercritical range between 1 and 4/3, which is called the sort of the Yahil solution, together with Guo, Hazik, and Schrecker. And it turns out that this self-similar solution and this self-similarity also has a very nice application in the general relativity setting. So in fact, recently we have shown the existence of these naked singularities for the Einstein-Euler system, really inspired by the Larson-Penston solution and some other, say, the work done by Ori Piran. So if I have time, I'll explain this problem as well. So for the rest of the time, let me now discuss the how we constructed these solutions to this Euler-Poisson system. And let me be clear that all of these solutions, once again, now will have the radial symmetry. So it's really spherical symmetric solutions to the Euler-Poisson system. So let me start with the dust-like collapse, right? Okay, so what is the dust collapse? So let me write down the Euler-Poisson system in spherical symmetry. So here, rho is now a function of t and r. So r is modulus of x, and then u is the radial velocity, and with the radial symmetry, one advantage is that now the gravitational force becomes extremely simple. So in fact, that the nabla phi term is indeed can be written by using this mass measured from the center to the shared radius r over r squared. So this is exactly the gravitational potential written in radial symmetry. And I actually deleted this pressure gradient term just to illustrate the solutions, right, in this case. So once again, let's see. So one way to see the solution, the behavior of solution to this problem is to introduce a Lagrangian coordinate. So in this case, let me think of as eta as a Lagrangian flow map, which is proportional to this R in line with this radial symmetry. And this chi is controlling, let's say, the either contraction or expansion. So for instance, if chi is less than 1, that means that my image in Eulerian image is shrinking, and chi is getting large, that means that my domain is actually spreading. Right. So then one can actually work out some detail, and the continuity equation, of course, mechanical point of view, this is really, the mass is transported along the flow map. So in fact, the Lagrangian density is simply given by the initial density divided by this Jacobian of the flow map, which is written in terms of chi in this fashion. And then using this form, the flow map here means that the eta dot time derivative of eta corresponding to the velocity u, and exactly chi dot will carry that. So then this the acceleration term is exactly given by the second derivative of chi, and then over here the mass due to the conservation of mass, and this is everything is carried as the mean density G over R here, exactly. And then the leftover from this flow map assumption will give me this chi square. So in fact, this pressureless Euler-Poisson system with the radial symmetry in Lagrangian coordinate is actually quite simple, and written elegantly like this. So then immediately, in the gravitational case, G over R is the mean density. So in fact, we see that this acceleration will always have the negative sign, right? Because this is positive and this is positive. So the acceleration is negative means that the chi will actually, under the certain assumptions, will actually try to go to 0, right? Because the force is going towards the center. And one can actually work out some details, and it turns out, interestingly, there will be a threshold velocity. So there is so-called escape velocity to this problem. So if the velocity is below this escape velocity, so it turns out that one can prove that chi will go to 0 in a finite time, which is the blow-up time. I call it as a T star R, so that the chi becomes 0. And then one can actually see that the blow-up rate near that blow-up time will be given by, say, 2/3 rate. And as I explained, so this means that chi going to 0 means that my domain will shrink, and moreover, my volume will go to 0. And this will drive my density go to infinity, right? So this actually illustrates the imploding solution and the blowing up solution driven by the gravity. And once again, this is the dust case, right? So we took the prototype profile, which is given by, let's say, the simple form. Since this is a genetic behavior, we just took it as a simple profile, which is given by 1 minus GRT to the 2/3, and GR is a function of the mean density like this. And for the moment, let's imagine that G is, let's say, decreasing, right? So for the moment, so in other words, let's suppose that initial density in the center is high, and then G is going like this, suppose, the mean density. So then this immediately tells us that the blow-up time, if I look at this blow-up time, which is exactly given by 1 over GR, and if the G of R is decreasing, then R equals 0, so blow-up time will be shorter. So in other words, gradually this will collapse starting from the center, and then it will continue to collapse. So call it as the continued gravitational collapse. So we assume that indeed G over R is a decreasing function to actually make use of this profile in the problem with the pressure. So now the theorem is that in this regime, gamma between 1 and 4/3, we show that there exists an infinite dimensional family of initial data, rho 0, u 0, omega 0, but again, I mentioned that it's all radial symmetric solution leading to gravitational collapse whose leading order behavior is given by exactly that profile that I mentioned. Again, these solutions, we studied this in the context of the vacuum free boundary value problem, and these are radially symmetric, and initial density, as I mentioned, is decreasing, and one can show that if initial density is decreasing, then the mean density will decrease as well. And also there is additional, let's say, assumption on the G, profile G, that the function related to the mean density, we indeed assume that they very flat near the center, so that this was actually quite important to construct the approximation solutions. So a few words about the proof. So I find it actually it's very, I mean, it's a lot of interesting ideas which went into the proof. So in fact, one may wonder, okay, pressure is very important, and also remember this pressure is the force that going against the gravity in some sense. So it's quite enemy if you want to construct some finite time blow-up solutions. So and also it is indeed, in terms of PD point of view, it comes as the highest order, say, contribution. So then it's really, I mean, how do we actually lift this the dust solution to the problem with pressure, right? So first step was we actually introduced this small parameter epsilon, indeed by using this the supercriticality of the gamma. So one can actually rescale the problem so that if there is an initial domain, so we actually shrink the domain so that the density, the amplitude will become high, etc. And then if we write the problem in the rescale variable, then turns out that exactly we will receive this small parameter epsilon. So we never send epsilon to 0, but it's just a small parameter that help us to close the estimate later on. So then our naive try was, okay, so because there is a small parameter, we let this epsilon to 0. So then the first approximation, okay, this is the pressure is the dust. So then we keep expanding. So analysis was done in the Lagrangian coordinate. So let's go to the Lagrangian coordinate. So then first dust, and then we plugging in this ansatz, and then to came up with the hierarchy of equations for this chi1 and chi-m. And it turns out that one can actually choose, specific initial or final data for these guys, so that eventually this next approximation, this guy can be made smaller than the original chi-dust profile, so that indeed everything here up to here can actually behave like a dust-like collapse. So this was possible once again due to this supercriticality, and also we needed to have that flatness condition near the center of the profile G. And sorry, then after so that,
you said you were choosing specific ones so that they would cancel. What if you choose the ones so that it blows up? Then what happens?
Oh yes, so then the other case will not work. Yes, so so in other words, here the scheme was that really, our motivation was to come up with really an example of blowing up solution, right? So indeed, we are actually choosing very carefully. So if we actually have the ODE, there are two possibilities to choose, but then we are choosing actually very specific one so that it indeed controlled and make smaller than this first approximation. So there is
but since you based all of this off of physical data or astrophysics that you mentioned at the beginning, shouldn't you probably be choosing something that actually physically makes sense?
Oh, this is, I mean, I think it's still a very legitimate solution. So in other words, indeed this chi solution, if we actually construct in this way, let's say, so then this chi, eventually we can actually construct up to that, let's say, the time of blow up, which is driven by this chi dust. So which means that chi dust and the next approximation. And then the key is, of course, now these are all like ODE solutions. Now, all the difficulty is embedded into the control of the remainder, which will solve the PD, right? So this actually, it's not really non-trivial. I mean, it is not a trivial step. The analysis of R is indeed quite non-trivial, but after all, if you believe me that this is all possible, in fact, this chi will be legitimate solution up to the really blow up time, and we are indeed constructing the smooth solution really up to the blow up time. Did I answer your question? So indeed, the physical, I mean, in this sense, it's actually good mathematical solution, which actually exhibit the finite time blow up. Along
I mean, it answered it. I just don't think that I agree, because if you're using data or physical from the beginning.
Oh, in that sense, okay. Okay, so okay, so this is related to, I guess, stability questions, right? Is that what you're asking?
Well, no, I'm asking, you mentioned in the beginning you're using physics, as in physics, the field astrophysics, to motivate this whole problem to begin with. And then it seems like at this step you're just throwing it all away, forgetting about it, and only using the mathematical techniques which you're describing here to motivate your analysis.
Yeah, so this is actually, well, this is like one methodology to construct a solution, right? But once again, what I want to say here is that this chi dust is a specific, and chi 1 will satisfy equation specific. And of course, this R, which actually carries this, let's say, the PD component, will indeed have this infinite dimensional setting, right? This is not a solution to the ODE, and it is a solution to PDE, right? And indeed, we are actually solving from, let's say, backward in some sense. So the final data problem to close everything. So once again, you know, I'm not really claiming that this dust-like collapse is indeed the physical solution, right? Here it's once again, as I mentioned that our motivation is to construct a rigorous, you know, the solution which exhibit this the finite time collapse. Yeah. So you can disagree, but yeah. So can I go on now? Okay, so let me go on. So this is about the dust-like collapse, and so then we were looking at these solutions, and actually, I don't know if the question raised by this audience maybe is related to this. So it turns out that the solution that I just discussed, the dust-like collapse, was not so easy to actually generalize to, let's say, the relativistic star, for instance. So we were led to a different regime, so which I will now start talking about. So this is, so the natural question is, okay, do there exist any other examples of collapse where all forces balance each other out? So in other words, dust collapse was really, we are really throwing away this pressure and then treating pressure as more like a secondary term, right? So then we were looking at this inertia and pressure gradient, and the gravity, and we're looking for some solutions where all the forces balance out. So this will come, for instance, as a self-similarity, say, solution. So we were looking into the physics literature, and it turns out that in astrophysical literature, this actually has been indeed studied a lot. So I was very amused and surprised by how actually rich the problem was in the astrophysics literature. So in fact, in gamma equal 1, the isothermal case, in 1969, Penston and Larson, they independently show numerically the existence of globally defined solution with only single sonic point present. So it's now known as the Larson-Penston solution. And in 1977, Hunter constructed other full discrete sequence of other smooth solution to this isothermal Euler-Poisson system. And in later 1988, 1998, and 2001, Ori Piran, Breno Witewski, and Maeda Harada, they indeed, based on the numerical study, they claim that these LP solutions are the only stable self-similar solutions, right? So we were looking at these physics literatures, and somehow they were indeed looking at this self-similar collapse, and then make the self-similarity hypothesis and believe that this is really a tractor, right, of the system. And in gamma between 6/5 and 4/3 in 1983, Yahil, he constructed again the numerical self-similar solution with finite energy. So we were looking at these physics papers, and somehow it was very nice. However, these papers really do some asymptotic analysis in some singular point of the system, and somehow just didn't see the rigorous proof. So we actually decided to construct these solutions rigorously. So now let me talk about this self-similar gravitational collapse. So the radially symmetry Euler-Poisson system, once again, I remind you, I just showed you this, and here I actually put the pressure gradient over here compared to the previous slide. And again, as I mentioned before, this has a scaling symmetry. So based on the scaling invariance, one can introduce this scaling transformation, and then to look for this similarity solution. So in other words, we just make this one as order of 1, so that we choose this lambda as the minus t to d, so 2 minus gamma, so that this becomes order of 1, so that I can actually put this quantity as the similarity variable y. And here, by the time translation symmetry, I'm thinking that now t equals 0 is the time of the collapse, and then maybe t equal -1 or any negative number could be initial say point, because they're similarity solutions, it doesn't matter. So then with this ansatz, now we introduce this similarity variable y, and then we look for the solution rho tr. We're plugging in this lambda and minus t to the -2 rho tilde, and then u as the minus t to the 1 minus gamma u tilde. And then we actually write the equation for rho tilde and u tilde. So then through this process, since now the dependence of the tr becomes really like y, right? So now from the PDE, now we go to the system of ODEs. So after dropping this tilde, and with this relative velocity omega, which is given by u plus 2 minus gamma times y over y, we get this system of ODEs. So this was written after some calculations, and maybe the specific form, which looks quite complicated, is not too important, right, for us now. But let me just try to highlight what are the what are the feature, right? Interesting feature to this system of ODEs. Or before that, let me actually make one comment, right? So then what does it have to do with this collapse solutions, with this rho tilde and u tilde? So from this ansatz, if we can actually have a smooth solution, let's say in particular rho tilde bounded and u tilde is bounded, let's say. So then as we can see, because of this factor minus t to the minus 2, when time approaches to 0, this will actually give us the blowing up solution, right? Imploding solution. So then the goal is, okay, we are interested in some solution where this rho tilde in particular is smooth and bounded. So then now, let's say we go back to this system of ODEs and we are interested in the smooth solutions, and we immediately see some problem because something in the denominator, right, appears. So the possible singularities of ODEs, as is apparent, in particular, this is first one is y equals 0. So when y is 0, then this because of 1 over y, and this will actually limit the behavior of omega near the origin, right? So this is the coordinate singularity, the center singularity. And more important singularity is this guy, which is now related to the concept of the sonic point. Since here, if you really think about, this is actually related to the sound speed square, and this is the velocity scale. So in fact, if this is positive, then flow is subsonic, and if this is 0, it's called sonic, and if this is negative, then it goes to supersonic. So now we can introduce to this concept, important concept, which is sonic point. So if the rho omega is a smooth solution to this self-similar or Euler-Poisson system, we say that the point y star, so that this the denominator to vanish is called the sonic point. So then why is it important, right? So in fact, one can do the Taylor expansion, since we are interested in the smooth solutions at the origin and far away infinity, y equal infinity, realize that this rho 0 and omega 0 will satisfy certain behavior. So in particular, near the origin, the omega will have a finite value, and center value also want to have a finite value. And then far field, this omega will behave like 2 minus gamma, and then this rho will decay like this, y to the minus 2 over 2 minus gamma. So if we believe that there exists a smooth solution, then it's now, if we look at this quantity, at the origin, this will be positive, right? Because y is 0, so this will be positive. And then far away infinity, because this will go to 0, and this will go to negative. So by intermediate value theorem, the flow, the smooth flow should pass this sonic point at least once, right? So the theorem, together with the Go and Haji with Schrecker, so we constructed smooth, in fact, real analytic Larson-Penston solution, gamma equal 1, with a certain behavior, in particular the desired behavior that I mentioned, and also gamma between 1 and 4/3. We show this polytropic analog of this LP solution. So for the next few minutes, let me describe the idea, right? And also, or maybe I should say a few words about this recent breakthrough by Moore, Raphael, Rodiansky, and Scheptel. So in fact, these imploding solutions are indeed possible for the Euler equations as well, without even gravity. So in fact, they developed this existence theory and finite codimension stability for this very smooth C-infinity self-similar imploding solutions. And over there also C infinite regularity is quite important in their analysis. So the one difference is that, of course, without gravity, there is a more invariant scaling. So in fact, the two parameter family of invariant scaling exists for the compressible Euler, and for the gravitational case, of course, gravity indeed fixed the self-similar exponent, so we have only one. And also the system of ODEs that we are getting is non-autonomous, right? So in fact, this unknown y, the variable, independent variable y appears in the system. So this actually makes the problem different. So let me now briefly discuss this existence of the LP solution. So gamma equal 1. So when gamma is 1, then it can be put into a rather simple, say, form like this. So in particular, the denominator.
I'm sorry, you mentioned some reference papers. So is this LP solution you're going to discuss was in the papers, or is it your work?
These LP solutions that I mentioned, this was discovered by Larson-Penston and then actually studied by many astrophysicists. So they constructed, or they claimed the construction based on the numerical. So it is a numerical solutions. So
okay,
here
so this is
we
their
are.
work. So this is their work.
Yeah. This one now is our work. So we are making rigorous. We are developing the strategy to actually have really existence of a real analytic solution.
So what did they have? They didn't do formula manipulation? Like what?
Or they didn't have a rigorous construction. They just did the expansion near the origin and near the Sony point, and then they claimed that okay, numerically they matched, right?
Okay, so there were no theoretical astrophysicists that you could find that did similar work?
Well, as far as we could find, we couldn't find any rigorous work.
Okay, thanks.
Okay, thank you. Okay, so then once again, this is the system of ODEs, and again the denominator doesn't depend on rho. And there exists once again the two explicit solution. One is the Friedman solution, which is the equilibrium of this dynamical system. So easy to find, and exactly it's a homogeneous density. And again, we want to have some, let's say, decaying solution infinity. So this is not the solution that we're looking for. And then also there exists the exact far-fetched solution, which is omega is given by 1 and rho is 1 over y squared. But of course here, I don't want this to go to infinity, especially near 0, because I want really bounded solution. So then in order to construct the smooth solution, the idea was actually to try to connect these two different behavior, right? So analysis is based on the nonlinear invariance of the flow to connect this Friedman solution to the far-field solution. So let me briefly describe the steps. So indeed, since the difficulty is that this sonic point y star, we expected that there is a sonic point, but the difficulty is that it's a priori, it's not known, right? We don't know what is the sonic point y star. So we make a guess.
I'm sorry, you just said that there were numerical analysis that you use from astrophysicists, that usually what physicists do is they find these critical points. How did you not know what the sonic point was then?
I mean, we don't have an analytic formula for y star, right? They have a numerical value of y star, but we don't know the existence. So we are proving such existence with mathematics.
So how did you choose the 2 to 3 that you have?
Yeah, this is actually educational guess. You have to actually look at the invariance of the dynamical system and then realize that 3 is a good number and 2 is a good number.
So you did not extract this from the physics papers?
Physics people actually, let me see. Well, you could say that, 2.3 something, right? So okay, so that's what the claim was. So you can
well,
say
maybe
that,
if that is something they claimed, you should put a reference to it that the people get credit for the work that they did. Just a suggestion.
okay.
I have a suggestion. Can you leave the discussion after the lecture?
I'm sorry for participating.
Oh, no, it's okay. But since I have to finish my talk, right? So you can ask me questions after the presentation. Is that okay? So indeed, I mean, in our paper, I believe we actually gave the credit to these astrophysics papers, right? Here we are presenting the mathematics, how we actually rigorously constructed the solutions, right? So I'm sorry that if you feel offended, but let me try to go on. So once again, with this educational guess between let's say this number 2 and 3, we indeed construct these local analytic solutions near the sonic point. So the hope is that we'll find the spatial value of y star so that it actually give us this smooth connection, right? And if we do that, we obtain really hierarchy of Taylor coefficient, and we use a combinatorial argument to prove this convergence of this series. And then once we have this local solution, it turns out that the flow is quite stable when we actually solve from, let's say, one point to the right of the system. So for any sonic point, which we are varying, say in this interval 2 to 3, we indeed, one can solve the system to the right, to the infinity, with the correct bound, and we use really the nonlinear invariances to the ODE system to show this. And perhaps more difficult or interesting part, where it indeed restricts this special value, it gives us a special value, is indeed to match to the origin, where we want to recover this very special behavior near the origin. So we call it as a Friedman connection. So we use this, develop the shooting method. So the idea is, okay, we'll try to find this y star bar to give us the limit of y0, it becomes 1/3, and then y goes to 0, it will actually stay above the Friedman curve. So let me just give you one picture. So the idea was that, okay, we realized that in fact this Friedman curve, where this omega becomes 1/3, is act as a kind of barrier. So we solve it, we vary this y star from let's say y star 3 to 2. So then due to that condition, Taylor expansion condition, in fact this will actually go down. It's decreasing initially like this. So then the idea was that there is a very nice argument, or the barrier argument, that once the flow goes down like this, or hitting this curve, Friedman curve, somehow it cannot really come back over here. So it will actually stay below this Friedman curve, so that this becomes a trapping region. So then our idea was that, okay, we actually vary this move this star, the y star value, to the left, so that it actually sliding down this behavior, so that indeed the meeting point exactly becomes the meeting point is really at the origin, so that it exactly stay above this Friedman curve to the interior. And one can actually prove that in the other side, also here, in fact, you will actually not touch this Friedman curve at all. So again, based on the invariant argument. So this is how we actually came up with this the existence of this special value of the y star bar. So okay, so I don't have much time, so let me actually try to now go quickly. So this can be also extended to Yahil solution, but as you can see, the system of equations actually considerably more complicated, and then realize that going from the quadratic to cubic equations actually is quite hard. There exists a Friedman solution and far-field solutions, but the challenges were really with these complicated polynomials. Somehow the invariance was not so easy to obtain. But this Schrecker, Matt Schrecker, he came up with some monotonicity argument for this omega. So in fact, he was able to, let's say, propagate this omega prime all the way to the origin, so that they gave us the monotonicity of this profile almost for free. So we have this existence. So for the remaining few minutes, let me just discuss this application to the GR, right, briefly. So the Einstein-Euler system take these forms. This is Einstein equations where the R mu is a rich curvature tensor, and R is the rich scalar curvature, and G is a metric, and T is the energy momentum tensor. So luckily, we have seen this Einstein equations in the first day of this workshop. So here we are interested in, once again, the perfect fluid. So the energy momentum tensor takes this form. P is the pressure, and the rho is the energy or mass density. And of course, in this Einstein-Euler system, actually unknowns are more, right, than just looking at the fluid variables. So it's the manifold M and metric, they are unknown, and density and pressure, they are unknown, and also there's velocity vector mu, they're unknown, which is normalized to -1. So here I'm taking the speed of light normalized as 1. And by Bianchi identity, one has this nice conservation law. So this is how we can see some connection, at least to me, to the fluid equations. And like in the gas dynamics, we have now we have equation of state. So we'll consider this linear equation of state. And this is quite acceptable in the relativistic gas dynamics, especially when the density is high. And when epsilon is zero, once again, this is exactly the dust case, so dust Einstein system. And by choosing this equation of state, really allows this invariant scaling into the problem, so that one can actually talk about the self-similar solutions. And by taking, let's say, trace of this system, I mean this Einstein equation, one obtains the rich scalar, the curvature, scalar curvature is given by 1 minus 3 epsilon times rho. So in this case, if rho blows up, then this curvature blows up if epsilon is different from 1/3, for instance. And one can write this Einstein-Euler system with radial symmetry by using this co-moving coordinates. So then metric G takes this form. So once again, the specific form at this stage is not so important, but I just want to point out that you can see the flavor of the Euler-Poisson system that I wrote down earlier with the radial symmetry in this setting. Of course, here, since the metrics are unknown as well, it's considerably more complicated, but in this co-moving coordinates, we have evolution equation of rho and the velocity v and metric, the coefficient lambda, etc. And some of them are really main evolution equations, and some others are constraint equations. And so, for instance, if we think of, let's look at this guy. So this actually is the momentum equation that we saw, right? In particular, in the dust case, I used the letter G for the mean density. So it actually has some flavor of the gas dynamics already if we use this co-moving coordinate. So co-moving coordinate is more like a Lagrangian point of view in the fluid the language. So again, the stellar collapse here is a big topic in this general relativity. So I just name a few. In fact, this dust solution, like I illustrated for the dust pressureless Euler-Poisson system, here also under certain assumptions, one can actually view this dust-Einstein equation as a ODE type solutions. So then, in fact, in even 1933, Lemaitre already, he actually wrote down a lot of like large class of solutions in this with similar ideas. And in fact, Oppenheimer, Schneider in 1939, they considered the space homogeneous densities, so which is particular subclass, and then described the gravitational collapse, which actually is known as the black hole type of solutions. And then Christodoulou in 1984, he showed that the Oppenheimer-Schneider behavior is indeed exceptional, and at least in this, the dust solutions, generic collapsing radial dust solution indeed form this naked, so-called naked singularity. So naked singularity means that informally, let's say far away observers here, they will actually see the singularities. So so it is a different like types of singularities, right? Which is related to the Penrose, let's say the cosmic censorship conjecture. So we were looking at this problem, and then of course, what about the collapse with the pressure, right? So there is a beautiful paper by Ori Piran, once again based on this numerics and formal syntactic analysis. So they actually showed the existence of this self-similar imploding solutions when epsilon is very, very small, which they call as a relativistic Larson-Penston solution. In fact, their insight was that after suitable rescaling, the self-similar solution indeed converges to the Newtonian analog when epsilon goes to 0, which is exactly the Larson-Penston solution that I discussed. And indeed, they actually, once again, numerically show that the singularity is indeed naked. And there are many other interesting work in physics literature. In terms of the rigorous construction for the naked singularities, other than these dust-Einstein equations, there is a work by Christodoulou in 1994 for the Einstein scalar equation with radial symmetry, and more recent work by Rodiansky and Schackbeck-Rothman in 2019 for the Einstein vacuum equations, right? So now let me, yes, I think I went over time, so I'll finish soon. So let me just describe the results. So we constructed this the relativistic Larson-Penston solution to Einstein-Euler system that I described with the curvature singularity at this scaling origin. So in other words, here it's like I show you the picture for the LP solution was we are looking at like more or less this part, but here we actually have an analytic extension. And then there is also massive singularity. And then we also studied the causal structure, show that there exists a null geodesic, so that outgoing null geodesic, so that the light can travel along this the geodesic far away to the infinity, null infinity. Once again, it's really inspired by the work by the Ori Piran. And one can actually flatten or dampen the profile at far away infinity, so that indeed it gives us the examples of naked singularity space-time. So I'm sorry that I went over time, but I managed it to the end of my slides. So I thank you for your attention. So I'll stop here. Thank you. Sorry that I had to rush.
So in the first part, you mentioned that the initial data that lead to the collapse is from infinite dimensions space. Can you describe the space? Is that like, does it form an open set?
No. It's a very good question. So no, actually we are not able to solve the problem from forward. So we actually, since the problem is actually unstable in some sense, so if we go to the forward, so we actually solve the final data problem. So we actually cannot really claim the stability.
But can you like up to some codimension, finite codimension?
Oh, that's a good question. Yeah, that's a good question. Yeah, so it's believed that, so actually I mentioned this flatness condition near the center, right? So in fact, what that means that the function that I introduced is G, which is related to mean density. We are assuming that, okay, it's flat, meaning that first many Taylor coefficient near the center become 0, right? So with the G of, let's say, R is like a G of 0 plus order of R to the say N, and N is quite big. So then, of course, this is a very specific behavior that we are requiring, right? So one can hope for this 4-dimensional stability, but it should be related to this, I think, the flatness index that we introduced. Yeah, but we didn't really go into let's say, this stability result for that dust problem.
Thank you.
Did I answer your question?
Yes.
Any other questions?
I just have a quick comment. I do apologize if my questions made you uncomfortable in any way.
I mean, yeah, sorry that maybe I should have, I don't know, cited more works. I don't know.
Okay, it seems there are no other questions. Let's thank the speaker again.